Okay, welcome back. I hope you are having, or perhaps you already, when you see it, the Thanksgiving is over, I suppose. I hope you had a good time. For this lecture, this is about October 13, which is the Monday. And perhaps when you see this, I am flying back to Korea if you see it on the class time. Anyhow, I'd like to finish the chapter 10. We have a fairly long list of computation. Not that difficult, but it's lengthy. So we are going to have two different cases. The first one is the acceleration parallel to the velocity. And later on, we also discuss acceleration perpendicular to the velocity. And we want to calculate the angular distribution and power. So for that, let's assume we want to talk about acceleration parallel to the velocity. So for that, we parameterize the velocity is certain number with certain direction, v hat, and the acceleration is also in the direction of the velocity. And then we introduce the angle between capital R hat and the unit vector of velocity to be cosine theta. And this was our original angular distribution in general, which was equation 10,154. And let's take a look at the numerator before square of it. So this is what we have. And if you take a look, first change v dot to be the acceleration magnitude times v unit. So this cross product to velocity itself will be gone. So we have a times v unit cross r unit that can be expanded like this, and then you get the first term to be cosine theta. R unit in the product R unit is unity, so you have this. So if you square it, you are squaring basically this whole thing, which you have cosine square theta plus 1 minus cross product 2 times cosine square theta, which is a square sine square theta. Okay, that's the step. And then you can replace those angular dependence to be this angular distribution in such a way that now you have this term. Now we want to talk about the distribution quantitatively as well as quantitatively. So we want to take a look first qualitatively. Let's look at the forward direction where theta is equal to 0. It's not exactly 0, but very closely to be 0. Then sine square, the numerator is approaching to 0. And denominator, when theta is 0, cosine is 0, but not exactly. This also is 1 minus beta. But depending on the beta, it will be finite value. So the radiation goes away at the forward direction. On the other hand, when beta is equal to 1, you can see that when cosine theta approaches to 1, this 1 minus beta cosine theta becomes very small number, but they are in the denominator. So overall power becomes enhanced at small theta. That's what's been discussed here. So you can see that there is some peak at certain angle, which we call theta max. And to get the theta max, what we are trying to do is to parameterize this term in the unit of, not in the unit of, it's a function of the angle theta. So we have sine theta squared and the denominator 1 minus beta cosine theta power of 5. And since we are talking about acceleration parallel, we introduced this parallel symbol. And we want to take a look, how does the angular distribution look like? And first of all, the answer is this. This is the case when beta is equal to 0. So peak is 90 degrees and 270 degrees. And if beta is becoming larger, the peak of angle is becoming forward. And when beta is 0.9, it's being extremely forward. And the homework I'd like you to try is to actually try to draw this using any program that you are familiar with. And by actually drawing these things yourself, you actually understand what's being drawn precisely. So that's the homework, and good luck. And I also draw this using Python package that I applied. Anyhow, so let's take a look at the relationship between theta max and the beta. So we replace cosine theta to be x, and you want to know where the maximum becomes. So obvious thing you can try is to differentiate. And require that slope to be 0. And looks complicated, but as far as the x is concerned, this is second order polynomial. So you can use this root formula that you must have memorized many times in your high school. So this is what I get. And x is bounded equal to or less than unity. So we chose to have plus. And then that's the relationship between beta and theta max for the maximum power. But to be super precise in mathematically, we are only taking the slope. We don't know whether this point is the maximum or minimum. And I leave you that to as the exercise that you want to do, perhaps, if you want to. Now let's get the approximate relationship between cosine theta max and at the end gamma. So for that, we express beta in terms of gamma, and you can expand for large gamma. So you can have this term and plug that beta into the cosine theta max term that we found, and it'll be looking very complicated, but you can first get rid of the square root by expanding this, and then you rearranged and then vector out 4, and this is what you get. And then you expanded this denominator at the end. So at the end you will get 1 minus 1 over 8 gamma squared when gamma is large enough so that we can neglect a higher order term. All right. In that case, cosine theta max is close to 1, and theta max is close to 0. And in that case, you can expand the cosine theta because theta max is small. It's 1 minus 1/2 theta max squared is the second order term. So you can say that theta max is now on the order of 1 over 2 gamma plus higher order term. So let's remember this. And in the limit, when theta is small and gamma is very large, then we can, remember, this is the angular term that we found for the case acceleration parallel to the velocity. And you can simplify this and further replace beta to gamma that we found in the previous slide. And then you rearrange and calculate the remaining stuff. And then you'll have this vector And then the angular part that we want to calculate is with this numerical factor. I have a gamma, actually 10 is split into 8 and gamma 2. Theta square is here, and in the denominator we have theta 1 plus theta square gamma square, and the whole thing is power of 5. Okay. Right. Okay. So note that in the case of acceleration anti-parallel, it's what you have to do is to replace a to minus a, but it's in the a square, so there's no change. Meaning when particle is accelerated or same effect decelerated, things are identical. So we can think about very high energy electron hitting a target. So that's a sudden deacceleration. And that situation is normally called, this is I think a German language, Bremsstrahlung. In English, it's braking radiation. So when a charged particle such as electron hits the target and the electron is stopped, then the radiation happens. And in that case, you can think about integrating over the all angles. And this is the angular distribution angle that you have to do. And so for the phi trivial, for theta, you have complicated integrand. So you can, what I did was to utilize Python package called the SymPy to do the symbolic integration. So that's what I get. And you can see that this is easily converted into this. So this integrand is this, and then your integral, not integrand, but integral becomes this factor at the end. So total power of parallel case is we have this factor, and things to note is perhaps charge square and the acceleration square and gamma power of 6. So that's the dependence that you have. Okay. And one more thing. So previously we have acceleration square and gamma power of 6, but now we want to recalculate in terms of change of the momentum. So we can use this formula, change of the momentum, to be m gamma 3 times acceleration. This was calculated some time ago for the case when for the relativist case. So we can have this so that we, by squaring it, we have a square gamma power of 6, which was exactly the term that we had in the total power. So now we can have total power for the acceleration parallel to the velocity in terms of all the constant, charge and everything is constant, and only momentum change square. So if you look at the total radiated power in terms of momentum change, it's proportional to the momentum change square. So let's remember this part because we want to compare with acceleration perpendicular to the velocity at the end. Okay, so that's all for the case when acceleration is parallel to the velocity. I went back, sorry. So now let's talk about the acceleration perpendicular to the velocity. This is the case, as you can see, this is the case with the circular motion. In the case of circular motion, acceleration is always toward to the center of the circle. So the velocity part and auxiliary part are perpendicular to each other. So for that, we want to parameterize v is v times z-axis. And we chose an x-axis as the direction of the acceleration to make a certain reference direction. And then we can introduce the pole angles, theta, phi, with respect to z-axis. And then we can parameterize r unit in terms of the spherical polar coordinate that we are familiar with. So this gives r dot v is cosine theta, and hopefully you remember this. This is the angular parts in the power in the numerator, and replace v and a. So we have this formula in terms of spherical coordinate. You want to square it, and you have this complicated dependence. So putting it all together, we have angular distribution of power, the usual factor, and the angular parts looks a little different from the case of acceleration, parallel to the velocity. And we put circle, CIRC, represent its circular motion instantaneously, at least, because all we want to assume is the acceleration perpendicular to the velocity at a given moment. So we want to define f now with the perpendicular symbol to be the term with only angular part, and we can integrate this to get the total power, and this is the result. Note that this is gamma power 4. Previously it was gamma power of 6. And a squared term remains as same in the case of the parallel case. And that's what I mentioned it here. And you can also draw the same meaning. We can try to draw this. And looks, when beta is 0, it has to be similar. No acceleration, no velocity, I'm sorry. And in the case of beta, it's 0.6, it's also going forward, but it's a little different. First, there's only one component, and there's some small structure in it, which we will discuss in a minute. So anyhow, we want to also express the total power in terms of the momentum change. Now we have gamma square and momentum change square. So gamma is normally greater than 1 for the relativist case, and for the circular case, when you have momentum change, the power radiation from the circular compared with parallel case is enhanced or larger by gamma power of 2. So in a sense, if charged particle moves a circular motion, it loses the energy by radiation larger in the circular motion. Okay? And from the previous case with angular distribution, you can get approximation for non-relativistic limit. Then you will have this expression easily. You can take a look, and it's called the cyclotron radiation. On the other end, if you go to super relativistic, meaning beta is close to 1, and the radiation is called synchrotron radiation. Those are cyclotron radiation and synchrotron radiations are terms commonly used in accelerator science. So in this case, gamma goes infinity, and let's think when theta is going to 0, because theta is forward. And then 1 minus beta cosine square is, you can have following approximation to have this simple formula. Therefore, the angular component that we have becomes this expression, giving us in total the angular distribution of the power for the circular motion when beta goes to 1 or super relativistic. Then you can approximate everything in terms of this. And this bracket, square bracket, becomes 0 when the second term is unity, or 1 plus theta gamma square is basically square root of this, which is 2 theta gamma, and absolute value of cosine phi. And you can solve for this. You can get theta gamma is cosine phi plus minus this formula. Okay, so this is my last slide. So this one has real solution only if cosine square phi is equal to 1. Therefore, when theta gamma is equal to 1, the distribution vanishes, for theta is 1 over gamma, and phi is 0, or phi is pi. So this is the plot for the same stuff. For beta is 0.6 and cosine phi is equal to 1. But we zoomed it. So we have this structure where it becomes 0, and it's approaching with the same angle as the previous one. But we have a smaller, what we call smaller lobe on the left, as you see. And you have to think a little bit to see if these correspond to the small ones, but it's kind of interesting to have this little lobe in the case of acceleration perpendicular to the velocity. Okay, that's all I have to say. When you use the slide, you tend to move faster compared with when you use the blackboard. So you are advised to follow each computational step to see if I made any mistake or not. Otherwise, you are not confident on each step. So that's perhaps what you want to do after you watch this. Okay, thank you very much. Bye-bye.